All right, so this is the second half of lecture 3. And I guess what was covered mostly was lecture outline is he talked about softmax and sigmoid and satellite imaging and you know, I guess multi-label classification here. And then just the last part of the lecture, he touched on the structured data stuff. But I guess the other thing is that on Monday, I guess 2 days from today, here, we're gonna start the online course in the evening, San Francisco time. And I believe this post here implies that he will make the recording available very soon afterwards. Let's see what he said, just like last time or something. Is
I cannot sit there and play with you.
I don't know who to mute here. Okay. All right, you know what? I just muted. So hopefully, I don't know, those of you who are awake can attend the course as it happens, and those of you who are asleep can wake up and have the video available. So the link for that, I guess, is somewhere in this post somehow. But yeah. For some reason.
I think the link also was sent by email to the registered users, I guess.
Oh, really? Okay. I guess I need to read my email more carefully.
In the email, there's a link to the live stream.
Yeah, live stream link is there. We got it a couple of days back, it seems.
Okay, great.
And did he say that they are immediately available, or do we have to wait some time?
I think he said very soon afterwards, or just like last time, which implies very soon afterwards. Not sure. I don't know what my login password is, but hopefully you guys can try this link. And then there he says, basically Jeremy's words were quote unquote, just like last time. And some students thought that would be immediately afterwards. Okay, so I guess I'm just going to talk about the, well, hopefully, did anyone have any problems with the exercises here? I guess the exercises being running the satellite image classifier. I had a lot of problems, but I guess the biggest problem I had was the download. I used to use Cressel, and that data was available pre-made for us. But I guess if you're on, I don't know, Amazon or other providers, Paperspace maybe, I'm not sure if that's available, so you have to download it. And the download was like 35 gigabytes. It took like 4 hours to download, I think. And even then, running the notebook, running a fit would, I think one of the longest ones would be like 4. When it was frozen, just training the last layer, it took like 4 minutes per epoch. So, and there was a last part of the exercise where you're supposed to unfreeze and train it, and so I didn't even bother doing that. It's just probably took too long. It's, you know, the whole thing probably would have taken at least 30 minutes to train.
Do we know which platform in the next version of the course Jeremy will suggest us to use?
I haven't heard anything. I'm assuming the same sort of platform as before. He kind of favored Amazon, so I'm guessing that's the same again.
So
Amazon Paperspace.
I mean, I guess it would be nice if he has the data already available somehow there locally.
Yeah, well, if it was Paperspace, yeah, I know that would be available, but I don't know about the other ones. I'm not Paperspace, Cressel.
Someone today asked a question on the forum that should we go ahead and set up AWS as suggested in the forum or wait? So Jeremy responded that we should wait for the first lecture before setting up AWS or anything.
Okay. Well, good.
I think they're still changing the library last minute, because so I've tried a couple of different environments. I've tried Google Cloud Platform, Colab, I've tried Salamander. None of them worked with the lesson 1 from the new course. I think they're still changing bits and pieces. So so you pretty much you have to update frequently to do that. So yeah.
But are they using the new version of the library for the Monday course, the course starting on Monday?
I was trying the new library, yeah, and because the lesson 1 is already available at GitHub.
Okay.
So I was trying to run it, but it didn't work for some reason.
Oh, okay. Yeah. All right. I guess I'm gonna try the new notebook this weekend then.
Hello?
Yeah, they changed cats and dogs to the different data sets. They now have like, I believe cats and dogs, but now also it's not only cat and dog, it's now like breeds as well. So different breeds of dogs and things like that. So it's a different data set, but similar concept.
Okay. All right. Well, we'll see. But I guess because it's happening in the lecture will be in about 2 days. I guess our next study group meetup. I guess we would target having watched those lectures and trying some, executing some of the notebooks and hopefully trying an exercise before we meet, because, after that it's going to be 2 days till lecture 2, so we don't have too much time. And we're going to pick up the pace, being 1 lecture, 1 week per video. So,
yeah, it's a good point. So next week we restarting with a new course, right?
Correct.
Yeah. Okay. Cool.
Yeah.
Cool.
And hopefully, there's some materials that we've already learned in this past 6 weeks. So, we should ease into that pace, hopefully, comfortably. All right. Any more things anybody else want to talk about? In the lecture, there was one bit of confusion for me, was softmax versus sigmoid. I guess when he was doing the spreadsheet, roughly at these type markers, he was talking about softmax, and softmax is if you want like it to pick out 1 class among many, or sigmoid if you want to use multi-labels for it, like 50% that it's a dog, it's 25% that it's a cat, 70, like 10% it's a boat or something. So those are the different activation functions. And the sigmoid only, the key is sigmoid only takes 1 input activation. Why did I say it's not weighted? Oh, yeah, well, before it came in, it was weighted, but, there's no weights in the activation function itself. I guess, single input, unweighted activations. Okay.
Yeah, Sebastian, by the way, I have kind of a nitpicky thing about sigmoid.
Yeah.
I think when Jeremy says sigmoid, he really means logistic function. Sigmoid is a general, it's a family of functions that have a few characteristics mathematically, and logistic is one of them. A sigmoid is something, you can look up sigmoid on Wikipedia, and it tells you it, has a non-negative derivative everywhere. It's bounded above and below, on the y-axis. And it has a value, a real value for all. I mean, it has a value for all real input values to the left and right on the x-axis. But
Right.
we should, and it caused some confusion actually at my workplace when we were writing some code. Yeah, just keep in mind, sigmoid is very commonly used, but almost everybody who uses that word means a logistic function, which does satisfy the requirements of the sigmoid family of functions. Jeremy will probably never make that distinction, but it's good to keep that in mind, I think, to be clear.
Okay. Thank you. Logistics is mistaken for sigmoid.
Yeah, well, they both have, I mean, logistic has the S shape like you see, like all sigmoid functions.
All right. Okay. The other thing that I found interesting is, we've only seen these neural networks as, basically 3 lines of code, right? Read in data, define your architecture, create a network, and then learn.fit. Yeah. But I guess one of the things he covered in class, learn.summary, that prints out all the layers in your network. I thought that was pretty cool. So that's handy to know. And when he printed out, I think we were doing a ResNet in this exercise, some sort of ResNet. And so it printed out a lot of layers. ResNet, I guess, having like 50 or more layers. So it was good to see, concrete evidence of that in our code.
And I thought it was interesting that Jeremy mentioned he doesn't like VGG. I guess we won't be using VGG anywhere because it has, I think he said 300 million parameters, maybe the last version of it, and 250 million of them are all weights in the fully connected layer or layers at the end. So that's kind of not the type of thing that he thinks is good for transfer learning. It sounds like with so much of the learning, the 2 or 3 weeks or more of learning that went into VGG was about that last layer. And if you're doing transfer learning, you really you're going to be doing a lot of changing of the last layer for your own particular problem, typically. So I guess he sees it's not that beneficial to use VGG for transfer learning.
Right. Yeah, that's a crazy amount of parameters. Was it von Neumann that said, like, if you give me 4 parameters, I can fit an elephant, and if you give me 5 parameters, I can make its tail wiggle?
Right. Yeah.
So 300 million parameters is a lot of elephants.
There was some paper that came out recently which said you can build a network with a very complicated deep network and then prune it and still get almost the same performance. But in their investigation, it was better just to start out with a sparser, smaller network to begin with. I think a lot of, who knows, in 5 years, we may be looking back and laughing at networks that have hundreds of millions of parameters because we will realize that all of them are much too large.
Yeah, what network is this that uses less parameters and then started to expand it?
In that paper, I think it was a method that they were outlining. I just read the abstract about a process of creating a sparse network, and for that particular example, they found that they could get a better performance than if you created a full deep network and then pruned it back like people do. Not one particular network, though.
Yeah, that's interesting because later I did a lot of I try to do a lot of research on ResNet here with all these hundreds of layers, and I found an interesting article I'll go over with you in a little bit that it give us a slightly different interpretation of these things and these layers. But yeah.
So There's an interesting article on towards data science. I've pasted a link on that on the chat if you want to show it.
Oh.
It shows comparison of different architectures, and indeed it shows VGG as being at the top right, which means very complex. It's on the chat if anyone wants to see it. It's been quite interesting. It shows the Inception v4, I think, being the best now. I wonder if Fast.ai supports Inception.
I suppose they can get it from PyTorch, maybe.
But when you say being the best, what do you mean for one particular problem?
Yeah, so indeed, based on that article, they've used certain like a measuring mechanism for that. So they use what they say. Yeah, that was the picture on the top. That was the picture on the top. Yeah, that's the one with the blobs windows. They use top one score, and then they define that metric in some way. So you're right. It's if you want to make this bigger, this image with the big, so this shows those different architectures.
The one with all the circles?
Yeah. So the top one accuracy is on the left on the y-axis, which means how good, based on that metric, the network is, and then on the x-axis you have like complexity, million of operations, I think, and then
okay.
the bigger the circle is, also it's like it also shows like complexity of. So VGG is like most to the right, which is very complex, but not really top performer. But there is a paper that it's linked in that article. So in that paper, they described what that top one accuracy means. But the ResNets are quite like not so complex and really quite well performing. So I guess that's why they were chosen. There seems to be Inception v4 is like getting the best score on the top one accuracy.
Oh, this is interesting. DenseNet, I'm a little bit familiar with. DenseNet is a lot like ResNet, except you have your input, projecting upwards into many layers.
What does the diameter of each circle represent? Is that parameters?
That sounds like it, because VGG is the biggest one. I think.
Yeah,
I
think the gray circles on the bottom.
The numbers down there, like
show you.
35 million, 65 million. That's the numbers.
Oh, right. Okay.
Numbers of parameters.
Yeah, there is an explanation of that in that paper. Let me try to find it. So there's that post on data science, and then there's a link to paper. Yeah, I can do it offline.
Okay, that's interesting. Inception, huh?
Yeah.
Let's see what else. Okay, so hopefully between let me just get back on track a little bit. Between in the next 2 days or something, hopefully you guys get a chance to go over the Rossman stuff. And there a lot of it, I guess lecture 4 leads into it. He covers a lot of that there, but the Rossman stuff is very interesting to me. I think it'd be good to learn some pandas. Anyways, well, let me tell you what I've been up to, unless anybody else want to share. I've been kind of researching ResNet, and it was really confusing to me. So I thought I'd inflict it upon you. Okay, so this ResNet's the thing we've been using all along in this past like 3 lectures, right? And so, what is it? What does it look like? Let's see. So hopefully you're familiar with AlexNet. AlexNet is basically 5 convolution layers. Here's layer 1, 2, oops, 5, and then like 3 max pool layers or something like that, and then a fully connected layer on top, right? So this is AlexNet. So I guess the thought for ResNet is like, if you can add more parameters, more weights, then it will perform better. It can, do more complicated functions, your classification functions. So the thought would be, okay, let's take ResNet and we will AlexNet and we will insert a bunch of convolution layers in here, and then maybe in here do the same. And so maybe that would be better. So I guess basically pretty much the Kai-Ming He is the lead mind behind ResNet. This is like a 12-minute video he has. He presented, and the key architectural stuff for ResNet is in this like 3-minute bit here. So if you feel like watching it, that's a good one to watch. It's a bit confusing for me. But basically, he has a very first he has a very modest goal, right? Let's add more weights and just make sure it doesn't suck. It doesn't make things worse. And when he did the experiment, if you plot like accuracy here. If you plot accuracy versus some training thing. So here's a normal, I guess here's a normal plain sort of like network AlexNet like, right? The accuracy. No, I'm sorry. You're not plotting accuracy. You're plotting error or something. The error goes down with training, and then. But if you add more layers, it should be like down here, right? But it's not. It turns out that this one is up here with more layers. Of this, right? Let me pull up his paper for a moment here. Do I have the paper? Okay, I don't have the paper handy.
Is it possible that the amount of data is important? If you don't have enough data, maybe more layers doesn't help?
Yeah, data is always, that is very possible. The more parameters you have, the more data you're supposed to have to fit it, right? That's, where? I have no idea where the paper is. Maybe we just look from here. Okay, here it is. Here's where. So you add, you're plotting error versus the number of training cycles or epochs, iterations. So, surprisingly, 56 layers here, your error is worse, right? So you add more layers and it sucks. So, the first thing you want to do is just make it not suck. And to do that, I mean, if you have this thing and if all this if all this thing does is just sort of like copy your activations from the bottom layer up, then theoretically, at this point, you're still, if you're going to compare it to the original AlexNet, at this point, after these extra layers, you still have the same activations. And likewise here, so you're still having the same activations here. And right here, you've inserted these 2 more layers, but all they're doing is copying the activations forward. So you're still having the same values as AlexNet. So it should behave the same way as AlexNet. You know, if you're just doing something stupid like just copying the activations forward. And he trained it and it didn't. So let's see. Oh, what did he do? So that's just a mod. Okay, so that's modest. Don't suck. So what we did was just we want to copy. We want to take a pre-trained. So basically, you know, in this experiment, in this thing I just drew, what you're doing is you're taking a pre-trained AlexNet, right? You're taking all the weights of it. You're adding these copying layers, and then you try to train it again, and you found out that it sucked. You know. So, but there, you know, there's a naive solution. How do you copy with this? Well, you know, if you're just doing some sort of convolution where it's just like the convolution that the weights might look like this, all it's doing is it's just copying a single pixel across, right? So that, and you take a stride of 1, so it's really copying. So that's a convolution version of copying your activations forward, right? So because it sucked, so what he tried to do next is he introduced a sort of a skip connection. So if you take 2 of these layers that you just created, you know, input goes in here, output here, and if you also, what you do is you copy this part. So this is your skip connection. It's basically doing a copy. It's a different way of copy. And then, so actually, before that skip connection, let me go back a little bit here. So he, you know, like one of these blocks here is that. So he trained this, and this is the one that sucked, right? It couldn't even do a copy correctly. So now he says, well, I'm going to force a copy by putting in this and forcing that copy, but this guy is going to roam freely in training. Well, not roam freely, but he's going to try to train this guy. So if you input X here and what you want is an output of X, remember your goal is just to not suck and copy, and you're forcing a copy here, then what's in this part is just like the error, and you want this guy to basically give you the 0 function, right? So then up here you would get X plus 0, and you've accomplished your copy. So he did this, and it worked well. So the key is the skip connection. The thing here, what you wanted to do, I guess the term they use here is you wanted to learn the identity function. You know, identity. You want to map X to X, but you know it couldn't do that right for some reason. It has problems learning weights of, you know, that weight of 0, 0, 0, 0, 1, 0, 0, 0, 1, for example. It had trouble learning this. But if you introduce this, then it has an easier time learning an all 0 or close to 0 convolution, right? So that's how you would do it. So your end goal is getting this to be, you know, is getting a set of convolution weights to be kind of close to that or something. And then it did better than just copy and not suck. You know, it did really well. It got better accuracies. You know, now the new accuracy with the skip connection is like down here, right? I think so. Basically, that's the idea behind ResNet to me.
So Sebastian, one question. So in other words, when it's doing better, right? It's not the identity. It's learning something there.
Right. It's close to the identity, I believe. Just like here. Well, in actuality, you know, it's close to 0. You have the skip connection that forces it to X, and this one is, you know, epsilon, right? So that's what it is, and I think it's close to that, but it does better. It's, you know, I think it's kind of, it's mysterious why it would do, you know, better.
So somehow it just can't directly learn X plus epsilon without this weird skip architecture?
right, without this weird skip architecture, we're back to this situation, and what you're doing is learning the identity, which is plain X, and it cannot do that. It's kind of mysterious to me. Lots of people try to reason it out. Like I was searching like why this is so, and I found a lot of explanations. Like here, I just put my notes up here. Like why did it suck, right? So here, some people thought that it's either vanishing gradients or vanishing data.
I really appreciate it. Thanks much.
In vanishing gradients, propagating your error backwards. The gradients are getting smaller because I think because with each, as you go, as you propagate that error backward further, the chain rule says there's more of these multiplications from the chain rule, and those multiplications are smaller numbers. So you multiply a bunch of smaller numbers, you get even smaller, so your gradients are vanishing. The other possibility is that it's vanishing, the vanishing activations on the forward pass. Those activations are getting close to zero. Maybe your weights are getting smaller, so those activations. I don't know. I was searching, and like, this is one of the Fast.ai students. He was proposing that. I'm not saying any of this is right here in this table here, right? But the originator of this thing, he mentions nothing about vanishing gradients. I don't know why people think it's vanishing gradients. All he says is, when you go deeper, it's the accuracy degrades. Vanishing accuracy, not really vanishing gradient. But it says the accuracy degrades, right? And then, another source, Andrew Ng's Coursera source, he says the lectures are about ResNet, and the first thing he says is deep neural networks are difficult to train because of vanishing and exploding gradients. So I don't know. Andrew Ng's, he opens with that, but he doesn't go on to elaborate or anything like that. So to me, he thinks that yes, the problem is vanishing gradients.
I think I don't even need a bag. I'll put it in here. Thanks.
Okay. Wow, that was the correct one. And then some, another student says it's not vanishing gradient. So there's all of this ping pong back and forth, And Wikipedia says yes, the problem is vanishing gradients. So there's no, I don't think there's a good explanation of why it cannot learn that identity mapping. There's a couple of interesting articles, particularly this one by Andre Veit. He's a professor at UC Berkeley with the Simons. I think he gave a lecture at the Simons Institute. I mentioned last time. He says the regional networks are not addressing the vanishing gradient problem. So I would tend to, my opinion is no, it's not a vanishing gradient problem, based on all this research I found. I think, let's see, I think he has an interesting interpretation of ResNet. Yeah, he says they behave more like, instead of having deep layers, he recasts them as having a bunch of shallow networks of some sort. And this is the diagram. I haven't read this really, so I don't know. But that's one interpretation instead of a deep network interpretation. Another interpretation of ResNet is this guy, from this guy, Tommaso Poggio. This gentleman is a physicist. He did a lot of neural networks in the second wave, along with Hinton and company. He published a lot of stuff there. So I think I tend to give him a lot of credence. So
can I add something?
Yeah.
Yeah, so I have taken this Andrew Ng course about ResNets.
Which course?
Andrew Ng course, which you have mentioned.
Oh, yes.
Yeah. So what I found is in his lectures, he has an explanation of how he thinks ResNet fixes the vanishing gradient problem.
Right.
Yeah. So what I recall, I have completed that specialization. So from what I recall, this skip connection provides a way so that at worst case, it can learn an identity function. So when you calculate gradients with backpropagation, identity function gradient will not reduce, gradient will remain constant.
Mm.
So at the worst, while doing a backpropagation in your network, with this skip connection, you can achieve a constant gradient loss. Like you don't have decreasing gradient. If at all your function needs to learn identity, it will have a zero gradient loss. So that's how it handles the vanishing gradient problem. I don't exactly recall the things, but I remember he giving a very detailed explanation about this.
Yeah. I think you know, hopefully, if anybody's interested, you can decide for yourself. This is the link to the 2 lectures. They're like 10 minutes each. So, but and I think what I recall from that is that if you're basically you have these additional residual blocks that you're adding, right? You add X into here, you want you get something out here, and some, you know, here R will stand for ReLU. I forgot his, but if you're taking a ReLU of Wx plus B, and so you're feeding this into here. There's a ReLU here. Is Wx plus B here. I think. Oh, and I think yeah, there was another layer. There's another Wx plus B here, and then you're gonna do the skip connection here, and then you feed it to another ReLU here. Then there's a couple more, but in the end, there's an X here, right? And I think what he said is because if you're using your L, if you're doing L2 regularization, which does some sort of weight decay, then this activation, you know, gets it gets smaller because your weights are getting smaller, your biases are getting smaller with this L2 regularization and weight decay. So in the end, what you're getting really is something that's very close to X, right? Which is what you want. So this is the explanation he gives for why this works. You know, it's not really, this does not address vanishing gradient, but that's all I can get from him from this 2 lectures. So you know, if you can.
I guess that may be a different lecture because yeah, I remember he talking about gradient and gradient calculations. Let me add to this doc once I revisit the lecture.
Yeah, I would appreciate that because
yeah,
it was very confusing to me. So if you can find something where Andrew Ng says something about gradient descent or not, I'd appreciate it.
Yeah, I will do it. Thanks.
Okay. But here's an interesting interpretation of the residual network, 150 layers, you know, 500 layers or whatever it is, right? So Tommaso Poggio says you can interpret that as this thing on the right. You know, your ResNet is on the left here, and like a recurrent ResNet in recurrent form is on the right. So if you do, and I guess we'll learn about this in future lectures. Jeremy will talk about it. But if you take a recurrent network, another way to view it is if you unroll it. That means you take each snapshot in time of what it's doing. So the bottom one would be like at time 0. The next layer up would be at time 1, and this would be at time 2. Then you can view recurrent neural network as this unfolded thing, and you can view ResNet, and you can use this this unfolding on ResNet, and you can interpret it that way as like a recurrent network. But to me, this is more sane than having 1,000 layers. So these notes are in my notes on Google Drive. So if anybody's interested, feel free to poke around. I'd appreciate any feedback. But for something that's supposed to be as simple as the identity function, I think there's a lot of confusion around it. You know, how do you do an identity function? Gee, isn't that an identity matrix? You know, if you want to learn identity matrix, can't you just set it? You know, force all your weights to be, you know, that some sort of identity convolution. But apparently, it's more complicated.
Yeah, I wonder if you could actually have a toy problem where you just have one layer, you know, one filter, and you reward the, you know, you reward the in the training process the network if it gives you back the same picture basically that it saw. Then I guess it should give you an identity filter, hopefully.
Yeah. I mean, the nice thing is when you're training this thing, I think, you know, you have an error here. You know what you know what you want. You want an X, right? You want X back, and whatever it spits out, say it spits out, you know, X tilde or something, then you can use this to get an error, and you know, propagate it back that way. As a matter of fact, let me just go over my notes. I kind of wrote something like that down. Yeah, so the way you interpret that skip connection is sort of like this, where H, you want this to be your identity function, and you want this to be as close to your 0 function as possible. So so you have what you want. You do your convolutions. You have what you get, and you subtract the two, and you can use that too.
Is this similar? Sorry, Sebastian. Is this similar to autoencoder? So it's multiple autoencoders that are training on subsets of the network. Do you think that's another partial, perhaps, interpretation of this? Where with an autoencoder, we're trying to learn a representation of the network.
I
typically,
see.
Yeah, typically it's not for an identity function. Maybe it's dimensionality reduction, but yeah, it just seems like it's similar to an autoencoder. But I just searched the paper there and I didn't see any reference to autoencoders. But
yeah, I think the end goal might be like an autoencoder type behavior. I guess autoencoder is like an like a content addressable memory. You encode it, and then when you decode it, you want to get the same thing back. So that's, you know, you encode it, decode it, get the same thing back. That's like the identity mapping. In that sense, I think that's likely an autoencoder result. But here we're not. I guess here we're just in autoencoder. You know, you have your encoder, and you have your decoder modules, right? And you go up here, and then, you know, when you get it back, you can down here. So there's a forward and backward passing between here. Whereas this residual module only goes in one direction. So in this sense, it's not an autoencoder.
Okay.
Yeah. I think that's all I have. Anybody want to share anything? Anybody found what we've done so far kind of interesting that you would like to go off in a tangent, take a deeper dive in some of this thing? You would like to, but you don't, you know, you may not have the time. So what's interesting for people so far? I'm just trying to suggest, you know, people might take a deep dive into some of the topics here. And and bless us with your research on it.
I think what's interesting to me, I don't know if I have the time, but it's what you mentioned earlier, Sebastian, around the viewing ResNets as not as solving the vanishing gradient problem, or solving that problem, but solving it by looking at networks or deep learning networks from the viewpoint of distances, where the actual activations are outputting a distance. And what ResNets are doing is minimizing that distance rather than minimizing the loss. So just a different interpretation, I think, which is interesting.
Minimizing the distance between what you want and what you got.
Yeah. So how I interpreted your description of that is that the outputs of the activations within, I don't recall the name of the paper that you mentioned, but that they are interpreted as distances. So what ResNet is doing, it's minimizing the distance in order to make a classification or in order to propagate activations through the network. So I'm not sure what part that was in the paper.
Yeah, this one, I think, you get a lot of sources on, of course, sources on the internet, and, some of them you don't know who to trust. I mean, it boils down to sometimes a problem of trusting which source you're looking at. This is the problem I had. So I found that, this gentleman here, Andre Veit, he's got some credibility, or Tommaso Poggio, he's got a lot of credibility. So, yeah. All right. Maybe yeah. I think the next, I guess, if we were to continue lectures 4, 5, and 6, then we go into the part that's really interesting to me is natural language processing. But I think we'll see what Jeremy covers first. Who knows? All right.
Yeah, regarding other things to look into deeper, I'm interested in the individual, well, in a lot of things, but maybe one of them is sort of these different kernel filters, like a 3x3 grid of numbers which detects edges, and there are lots of variety things, filters like that. Some of them, detect horizontal lines or curves or vertical lines, or sharpen an image or make an image more blurry. And it would be interesting to look more into that, and maybe, in fact, try to come up with some filters that do interesting things that aren't already known about.
Mm. There's these handcrafted filters that people, before, I guess before neural network got popular again, we're doing these. There's a library called SIFT, S-I-F-T, a library of filters there. I don't know what those filters are doing, but I just know that some of these filter libraries exist. Apparently it didn't work as well as neural nets. Yeah.
Right. Well, I mean, in the context of a deep neural net, these little filters that we're using, that all of these AlexNet and ImageNet and Inception are using. I guess I'd like to do a bit of a deeper dive into into what variety of filters there are there, and what they're doing, and what other sorts of filters can be created. I mean, you can, yeah, for example, you can sort of just randomly try to create different types of filters and tweak them to go into the direction you want them to go, and ignore the you know, all the layers except the one before and after the filter you're interested in, sort of, so you can train it exactly to do what you want to do. Anyway, there are probably a lot of unexplored things in the area of these individual filters.
Well, here's another well, I think it's unexplored area is you can apply these kernels to language processing. So instead of, you know, typically language processing uses a recurrent neural network. In the last study group, we explored how these convolutions are used to process, you know, used to learn languages. So kind of like serial data, convolution on time series data instead of on, you know, two-dimensional images. So what those filters are doing there sounds pretty intriguing to me. You know.
In fact, Jeremy mentioned in the one of the videos that we've seen, he doesn't know why almost nobody is looking at transfer learning in language processing context. And then earlier this year, I think it was, he and someone else had wrote a paper and a blog post about, I think it's called UML Fit, which is, I think, exactly that. You know, he mentioned it in the course of something that was unexplored. And then within a year, he and someone, yeah, Abhishek says it's UML Fit. He and somebody actually did that. So that's, yeah, maybe he'll mention a few other interesting unexplored ideas. That's one good thing. That's one of the reasons that, you know, somebody getting a master's degree or PhD has an advisor. The advisor knows enough to tell them what are some interesting unexplored areas that are accessible and ready for exploration.
Yes, it's ripe for the picking. Yeah, I think that UML fit, Universal Language Model fit, I believe it's in the version 1 library that we're going to use. I think, if I recall Sam's interview with Jeremy correctly, and so that would be nice. I would like to try that.
It might be covered as well in this course in the coming weeks.
Oh, awesome, coolness. Yeah, so it's, you know, it's an interest, it's an area of interest for Jeremy. So hopefully we'll talk about it more.
So what is the plan for the new session starting from 22? So
the plan is to watch it on Monday or Tuesday, and then do as much as you can during the week, and then we'll talk about it Saturday morning, my Saturday anyways, and hopefully you've gotten, you know, 80% of that lecture done or tried, 80% or more.
Sure.
Yeah.
Go on.
Sorry, go ahead.
I just wanted to say about the different environments. So the guy who runs Salamander, he just replied that he will update the Salamander environment to the latest Fast.ai library, so should work from Monday. So if anyone still needs to choose one, this seems to be at least a good option. I'm going to try it.
Oh, cool. Yeah, I mean, you know, environment, you know, with the 1 lecture per week pace, you know, you don't have time to mess around with your environment. You know, that can drag on for a long time. So any platform like Salamander or Cressel that has data already for you, has the libraries, you know, installed for you, you know, that's a big plus.
What is Salamander?
It's another option. It's quite easy to set up. I think they do it on, they use AWS spot instances, so you get good price, cheaper than Paperspace, cheaper than AWS, and it's basically installed by clicking it's basically easy to set up. I just set it up this morning, and it took me like a couple of minutes to start running. So it's an option to try for sure. But I'm not sure exactly which option Jeremy is going to recommend during the course. That's kind of, the last time that was Paperspace and Cressel, but I don't know what's going to be this time.
Well, I used Cressel this month, and it worked very well, except there were some deprecated error or warnings here and there. So I'm likely to try whatever he suggests. Maybe things will already be loaded and ready to go and just work out of the box.
Oh, hey, Tony, so you tried Cressel. Have you tried, switching, like doing a simple one like dog versus cat, switching from GPU to CPU to see if there's any improvement? Because when I did it, there was no difference.
Oh, no, I didn't do that.
Okay. Yeah, let me know if you decide to. I'm curious if it was just me or that day where all the Cressel's GPUs were out and they just funneling us over to CPU land.
Oh yeah, that they should make you aware of that since you're paying money.
Yeah.
That could happen.
Yeah, it's very, I don't know, you probably noticed, it's very easy to switch from CPU to GPU, right? Even when you log in, I think there's a button, there's a little toggle button for GPU, CPU.
But I think I remember Jeremy said Cressel was much slower than some other platforms, right?
Yeah. Before I let you guys off, the gentleman that asked me about distances, the gentleman with an Irish accent, who is that?
Hi, my name is Adrian.
Oh, hey. Yeah, I asked because I lived in Ireland for a little bit. So.
Oh, okay.
It's a secret longing of mine.
All right, cool. Yeah, I'm based in the west of Ireland.
Okay.
Mayo. Yeah, I was asking you about distances, and I just wanted to ask as well, did you have a question to ask me?
No, that was my question. I just want to know who you were.
All right. Oh, okay. Yeah, Adrian Ornane. So I'm wondering about the new course that's coming up. Is that going to be recorded, or is that I know it's going to be recorded, but is it going to be made available for European-based people, or what's the?
I think it's available on YouTube, so it's available to everyone.
No. Have you subscribed for part 3, part 1, version 3?
But I think it's not clear if it's really going to be available immediately.
No.
He said that.
I am part of last year Fast.ai. So it is something like you will have a live YouTube session, and immediately after the session, there will be a YouTube link posted in forums.
Very good.
That is supposed to be private, only for the people who have registered.
Okay, so there's your quick answer, Adrian. It's available in Europe if you registered.
Yeah.
Okay.
Yes.
And is it okay? Is it too late to register now? You can just sign up today and we'll get that link.
Yeah, registration date is done. Yeah.
No, I think they took down the registration page.
Yeah. It's done.
It was October 12th, the deadline. But I think the link, I think the video is available to anyone who knows the link, but I don't know how that works.
Yeah, I think so.
Hey, Adrian, hit me up later, and I think I can figure out a way for you to watch it.
In the
And
email it was
video,
mentioned.
I think Jeremy had a comment that said, "Don't give this link to anyone who's not registered."
I didn't see that one.
Okay.
Also, in the email it was mentioned they are going to do away from YouTube after lesson 1. In the link which came, they are going to post another thing in forum.
All right, very good. Okay, I guess hopefully you guys will find some time on Monday evening or Tuesday morning, and then we'll talk back in a week and see how that lecture went. All right? All right, thank you, everyone. Have a great weekend.
Yeah, thanks, bye.
Thank you.
Bye. Bye. Thanks.
Bye. Thank you.